Hello everybody, welcome to 4.1 Part 1, Properties of Mathematical Systems Introduction. Every mathematical system you've ever worked with has obeyed the properties we are going to look at in this chapter. The commutative property. Multiplication is commutative. You can multiply two numbers in any order. A times B is equal to B times A. Look at an individual example like 3 times 4 is equal to 12, but so is 4 times 3. Or look at a multiplication table and see that it is true for all numbers, since the answers are the same on each side of the diagonal. So here we are, for example, here's a multiplication table, and if we draw a diagonal down this multiplication table, we see that the answers here on this side of the table are the same as they are here. That means they are commutative. Add two numbers in any order, A plus B is equal to B plus A. But subtraction and division are not commutative. For example, 5 minus 8 is equal to negative 3, but 8 minus 5 is equal to positive 3. Similarly, for division, 12 divided by 6 is equal to 2, but 6 divided by 12 is 1/2. We can invent our own operation and see if it is commutative. In example 1, we're going to do this. The operation hand takes a number, adds it to 3, then adds it to the other number. We can describe this algebraically as x hand y is equal to x plus 3 plus y. Is this operation commutative? Let us try an example. So 7 hand 2, that means we're going to make x equal to 7 and y is equal to 2, and then we're going to substitute on the other side where x is, we'll put a 7, and where y is, we'll put a 2. So we end up with 7 plus 3 plus 2, and that gives us 12. Now let's switch it around and make x equal to 2 and y is equal to 7. And that means that it will be, when we substitute it, that we will have 2 plus 3 plus 7, and that is also equal to 12. We can see that hand is commutative since either order gives us 12 for the answer. In example number 2, the operation box takes a number, doubles it, then adds it to the other number. We can describe this algebraically as x box y is equal to 2x plus y. Is this operation commutative? Well, let us try an example. 5 box 3, so I'm going to call x 5 and y 3, and then I'm going to substitute wherever I see x 5, and wherever I see y, I'm going to substitute 3. So I end up with, for this particular operation, 2 times 5 plus 3, and that means it's equal to 13. Now I'm going to reverse it. I'm going to now call x 3 and y 5. And that means when I substitute x and y, I will get 2 times 3 plus 5, and that will give me 11. We can see that box is not commutative, since one order gives us 13, while the other way around gives us 11. Example number 3, operation table for smiley face. So here we have our table for smiley face. We're going to consider the mathematical system with elements A, B, C, and D, and the operation is denoted by smiley face. And the squiggly brackets, or the curly brackets, mean that these represent the set of elements that are in this table as on the sides here. This operation table shows how operation smiley face combines with any two elements. To use the table to find C smiley face D, we locate C on the left-hand side and D on the top. The row and column intersect, as you can see by the yellow arrows, at B. So therefore, C smiley face D is equal to B. We want to define certain properties on this table, the first of which is called the closure property. For a system to be closed under an operation, the answer to any possible combination of elements from the system must be in the set of elements. Well, what this means is here is our smiley face operation table, and that means here we have A, B, C, D, A, B, C, D, and we look in the body of the table here, meaning inside here, and we see, is there any other elements in here besides A, B, C, D? Well, we see that the only elements inside here are A, B, C, or D. That means that it is closed. It does not have any outside elements. So this system is closed. All the letters are in the body of the table without any outside letters or elements. Another property we're going to look at is the commutative property. We already looked at this a little bit earlier, but in general, for a system to have the commutative property, it must be true that any elements x and y from a set x smiley face y is equal to y smiley face x. And it's this particular set we're going to look at here. So let's go back to our table. And here we have the smiley face operation table. How are we going to figure out whether or not it's commutative? Well, we're going to do the same thing that we did earlier. We're going to draw a diagonal through it. If we draw a line from the upper left to the lower right, we could fold the table along this line and have the corresponding elements match. So as you see, if we fold it, B will match B, C will match C, A will match A, D will match D, etc. The system has the commutative property, and that's what that would mean. If they match up by folding, then they have the commutative property. This is called symmetry with respect to the diagonal line. The next property we're going to discuss is the associative property. For a system to have the associative property, it must be true that any elements x, y, and z from the set, in our case, x smiley face, bracket y smiley face z, close bracket, is equal to bracket x smiley face y, close bracket, smiley face z. So let's look at our table. And it turns out that there's no really quick and easy way to do this, meaning we can't just draw a diagonal or inspect it. So what we have to do is we have to work out a few cases. So let us work out a few cases. Here's one case, A, B, C, and I put the brackets here around the B and C, and then I changed it and put the brackets around the A and B. So what I want to do is I want to check using our order of operations to see if this is true. So let us do the first one. I have here, I do the operation B smiley face C first. So I go to my table and I go to B and see where they intersect, and I see they intersect at A. So I put an A over here. And now I have A smiley face A, and then I do the same thing, A smiley face A, and I see where they intersect here, and I see they intersect at A. For the next one here, I do the same thing, but instead I start with A smiley face B, because that's in the brackets, based in our order of operation. So I go to A, B, and I see that A, B intersect at B. And I end up with B, smiley face C. So I go to B, smiley face C, and I see, indeed, I get A. Since both give me A, that means that it is associative in this case. Let us try another example and see if it's associative in another case. So now I'm going to use B, D, and A. I have D smiley face A in the bracket on this side, and on this side I have B smiley face D in the bracket. And I want to check to see if I get the same answer no matter how I bracket it. So we look at our order of operations. That means we do the bracket first. So we do D smiley face A. So here we have D, here we have A, and we see it intersects at D. And we put D. And so we end up with B smiley face D. Now we look at B smiley face D, and we see that it intersects at C. Similarly, we do for the other one. B smiley face D we do first. So we go to B, D, and we see it intersects at C, so we get C smiley face A. Now we go to C and A, and we see it intersects at C. And in both cases, we get C. So that means it's associative in this example. So we will assume the operation of smiley face is associative. The next property we're going to discuss is the identity property. For the identity property to hold, there must be an element E in the set such that any element X in the set is X smiley face E is equal to X, and E smiley face X is equal to X in our particular case. So let's look at our smiley face operation table. And we see A is the identity element of the set. So meaning that when we do the operation of smiley face using A on another letter, that means we get back that letter. So in the case A to A, we get back A. B smiley face A, we get back B. C smiley face A, we get back C. D smiley face A, we get back D. This can also be done by inspection. Notice how this column and this column are identical. Notice how this row and this row are identical. So we see how the top and the first row are the same, and the left and the first column are the same. This means that A, because A is the one that is on top here and on the side here, is the identity element. The next property we're going to talk about is the inverse property. If there is an inverse in the system, then any element X in the system, there is an element Y, the inverse of X in the system, such that X smiley face Y is equal to E, and Y smiley face X is equal to E in our particular operation, where E is the identity element, and in our case, it's A. So let's look at our table. If every row has the identity element, it also has an inverse. So here we have the identity element in the first row. Here we have the identity element in the second row. Here we have the identity element in the third row. And here we have the identity element in the fourth row, meaning each letter has a multiple that gives us A. So in this case, A smiley face A gives us A, and here we do that intersection. B smiley face C gives us A. That's where they intersect to give us A. C smiley face B gives us A. And finally, D smiley face D, and there they intersect at A. To summarize what we just did, we let A, B, C, and D be the elements from the set of any system, and smiley face represent the operation of the system. We found that the property of closure is true since A, B, C, and D are in the set and no other outside elements are in the body of the table. We found that it is commutative because A smiley face B is equal to B smiley face A, symmetry along the diagonal. We found that it is associative because A smiley face B smiley face C, that no matter where we put the bracket, we still get the same answer. We found that there exists an identity, meaning that whatever we multiply A by will get back the other element. And we found that there is an inverse, meaning that we can get back the identity element. Thank you very much. Be well, take care, and goodbye for now.